A system is called causal. A system is a causal system if its impulse response is 0 before time 0. After time 0, things can happen. Before time 0, sorry, no response. Okay, so that's the idea of a system being causal. A system only produces output right at the moment or after the system receives an input. Okay, before the system receives any input, it doesn't spontaneously produce any output. That doesn't happen. Okay, causal. 这样有没有一点感觉 cause because the system has a cause, then it produces response. Okay, so just to simply draw a picture, an h of n might look like this. H of n at time 0, there is a response, and then later the response can last for a few moments or indefinitely. Okay, but any time before time 0, everything should be 0. No response before time 0. What is time 0? Time 0 is the moment the system receives the delta function. Okay, so delta function. Okay, let's emphasize again what's impulse response. Impulse response is the response that the system produces when it receives the delta function. Okay, no response before time 0. Okay? Before delta comes in. Okay. All right. So with that definition, let me mention that in this course we're mostly interested in systems that are causal. Indeed. We are interested in systems that are causal most of the time. And we'll learn how to analyze a causal system, and we will also design causal systems. And when we say design, it means that we want to meet certain performance specifications, specifications. So far, so good? Yeah, causality. Okay, causality. And here's a note. So if we know that a system, an LTI system is causal, then this convolution equation can be slightly modified. Okay, let me explain. Y is equal to flip h and multiply with x. That looks like a convolution for sure. But now the index only runs from minus infinity to n, to the current moment. Okay? You know that before, in the previous slide, what is this index? In the previous slide, in a more general discussion, when we convolve two signals in time, that means we run the index from minus infinity to infinity. Okay, the k here, the k inside, can run to plus infinity. But here we can stop at time n. To evaluate y of n, if n is represent the current moment, at any moment to evaluate the output, we only need the index to run from long before, for a long time ago, all the way to the present moment. Why? Because the current output does not, the present output, 现在, the current output will not depend on the future. The system, the future will not affect the current output. That's the spirit. 这是一个它的精神在这里啊。Yeah, that's the spirit. So that's why here you can just stop at n, because for any k bigger than n, for any k later than n, right? You immediately notice that what happened to this term. This term here will be 0 for all negative time indexes, right? So nothing in the future will affect the current output. That's the idea. Okay, is that clear? So this one little nice thing right here. Stop at time n. There are actually so many ways to look at this equation. You can also think of this as if when we receive an x of n as our input, or let me say x of k, okay? Yeah, k equals to, so here you have an input signal and so on, okay? And then what is the output? The output at any moment n Okay? The output at any moment n is a summation. It's a summation from all the influences it receives from the past. K is the past, right? K runs from all the way long ago to right now, right? So that's the entire history. The entire history of the input would affect yn in a linear way, and this h is the linear coefficient. That's another way to think about it. Okay? Every past input would just affect the current output, and we sum them up. That's the way we calculate the output. Okay? Anything in the past can affect the current output. That's the idea. And with different weighting, okay, with different weighting. So each weight is represented in h. The impulse response will tell you how to calculate this summation. Yeah. So there's so many ways to ponder and contemplate on the result. I like the word contemplation. 凝视一下, contemplate your result. It makes a lot of sense, right? We cool? Yeah. 可以吗？好。那 with this, let's look at an example. Okay, so in this lecture, probably not in this lecture, but starting next lecture when we talk about difference equations. An important class of causal LTI systems can be defined by difference equations. 差分方程, sorry, not 微分, 差分方程. So here is an example that we will actually look at later, probably next hour. Difference equation. Okay, so here we have the current sample y of n. Right? Every current sample now depends on the past in this way. You sum of the previous two samples, and probably the system also keeps receiving input x. Right? So this defines a system. Okay, it receives input right here. It produces output like recursively. There's also feedback terms, okay, if you will. 如果你这样说的话，也说得通啊。If you will, the output is the summation of two past samples plus any input that the system receives. So that's a system for sure. Input, output, receiving input produces output. But then we can question. We can question: is this system linear? Is it time invariant? Is it causal? Yeah. So what's your opinion? Is this system linear? Is it time invariant? Is it causal? These are valid questions, right? These are concepts that we just learned: linear and time invariance and causality, right? Is it linear? Is it linear? If you double the input, will the output also double? No, you can check these properties. Okay, seriously. So you can check whether the system is linear. Okay, the answer is yes. Okay, and is it time invariant? If we delay the input by 3 samples, will the output also be delayed by 3 samples? Right? Is it time invariant? Right? Is it time invariant? Okay. Yeah. So these are the questions that we can look at. And here, the equation specifies a system, right? Then we can immediately ask. We can immediately question: linear, time invariant, or is it causal? Is it causal? Does this equation produce any output before it receives any input? If the input is delta function, then does this equation produce any output before time 0? Yes or no? Yes or no? Okay. Anyway, so more general, this is just one example. This is just one example. But more generally, we'll study what is called linear constant coefficients difference equations. Okay, in the next lecture, where constant coefficients means that here we have coefficient 1, 2, 3. We have 3 different coefficients. They happen to all be 1. 系数刚好都是1的. So you can change you can generalize from here. the coefficients does not need to be 1. Okay, it could be any arbitrary real number. Okay, so in that case, we have different difference equations with coefficients, with constant coefficients, and we studied that. Okay, my answer to this, my short answer is indeed this system is linear, it is time invariant, and I would like to say it's also causal. Okay, yeah. I would like to say it's also causal, unless you are super creative. We'll cover that in the next hour, right? So this is an example of a linear system, time invariant, and we can see it as a causal system, right? We'll come back to this, right? But next topic, let's officially introduce the Z transform, the Z transform. Okay, so we study Z transform. There's a reason why. The reason mainly is because we want to analyze the behavior of linear time invariant systems. So this is a tool. Okay, Z transform helps us understand and analyze properties of a LTI system. So we need to first let's move on to talk about the definition. Okay. So the definition is transform. So for any given sequence in time, n is a time index. Okay, for any sequence in time denoted as p, p of n, and n is an integer valued index. Okay, n is integer. So we can attempt to evaluate this expression. Okay, well, let's define this expression. We have a summation right here, and p goes here, z goes there, right? So the result, you just for any sequence p, small p, in the time domain, we have a corresponding function of z, a function of z. And what is z? Z in most generally can be any complex number. Okay, any complex number, and the summation index it sums over all n. Okay, so Pn can be from negative infinity to plus infinity. Okay. So I said this is an attempt to evaluate you can write down the expression. You can write it down. You can write it down. But I say we can attempt to evaluate the expression. That means that sometimes this infinite sum does not converge. It does not always converge. So let me say so. Okay. Of course, you can write down the expression, but it does not always converge. It depends on a few things. Okay. But first thing first, that's an expression. You can write it down. Yeah. Right. So we say that P of z, the big P, still we keep this convention using capital letters for the functions after transformation. This is a transform, much like it has a relation with Fourier transform. Okay, it's a transform. It goes from time domain to the Z domain. Okay, transform, the capital letter 大写, capital letter for the transform domain, and it's indeed called the Z transform of Pn, small p in the time domain. And this expression, 这边有点咬文嚼字, so let me read it. This expression is well defined only over the region where this equation converges, right? Otherwise, it does not make sense. Otherwise, it's just you write things down. Okay, it does not make sense. This really, because we really want this to be a function of z, receiving, you can evaluate the transform at any one point on the complex plane. But sometimes it doesn't converge. Okay? It doesn't converge. There are a few criterions for if we consider convergence. Okay, but right now I just want to just show you that the expression itself is pretty simple. Okay, for now, let's not worry at this moment for the region of convergence for right now. But I do need to emphasize that it does not always converge. Okay, depending on where z is and depending on property of p of n. Okay, we come back to that later. Any questions so far? Z transform regarding its definition is an expression. Okay. And here is a remark about the notation. Yeah, there is a relation between Z transform and the DTFT, the discrete time Fourier transform. Okay, so let me read it. DTFT really is the Z transform evaluated on the unit circle. DTFT is equals to Z transform evaluated on the unit circle. Okay, what is the unit circle? Unit circle is the circle with radius 1, okay, around the origin. Okay, so maybe I can draw a few pictures right here. So suppose this is a complex plane. We have the real part and the imaginary part. So the unit circle is a circle with 0, with origin being the center, and 1 being the radius,半径 or radius. Radius equals to 1, so you just draw a circle, the best you can, okay? Something like that. With a radius, topologically, this is a circle. Bear with me. 拓扑学上是一个 circle. Anyway, you get the idea. With a radius 1, so that's a unit circle. Okay, so I use this notation. I use the curly bracket, 大括弧. I use the curly bracket to denote a set. So here we have a set of points Z that can be parameterized by e to the j omega. Omega is the angle. Omega being the angle, right? So e to the j omega is a complex number which has a radius of 1, which is 1 from. It has a distance of 1 from the origin. Okay, so this is a unit circle. It's called a unit circle because the radius is 1 unit. A unit circle. Okay. So what does this mean? We say DTFT is Z transform evaluated on the unit circle. Why? Let's take a look. Okay, it's rather simple. That means when we evaluate the Z transform of X, the signal, on the unit circle by making the substitution, right? Z here just makes a substitution. Z equals to ej omega. That's what we mean. 在 unit circle 上面测量 Z transform or evaluated. Z transform when evaluated on the unit circle, yeah, just make the substitution, then you get this. Then you get this. And what is this? This is our friend, our good old friend, DTFT, right? Exactly the same. Simply by replacing Z with e to the j omega, right? So it's a substitution. We are evaluating Z transform if it converges, okay, only if it converges on the unit circle. Otherwise, the entire thing does not make sense, okay? But when DTFT exists, then we say when we need to add this criterion, okay? When the DTFT of the signal exists, when this expression and that expression really converges, when this expression really converges, then it equal to Z transform evaluated on with that substitution. 代入一下就可以了. With that substitution, Z transform evaluated on the unit circle equals to the signal's DTFT. And that's really nice. So that explains one strange thing right here, okay? In the textbook, you remember all the way in chapter 4, you've turned in the homework number 1, right? We recommend that we use this notation, big X spectrum, right? But inside, what do we put inside? We've been putting like rather inconveniently, 有点不方便了, rather inconveniently. Inside, we put e to j omega. Why don't we just denote spectrum as x of omega? It's a spectrum, it's a frequency, it's a function defined on the frequency domain, right? So why don't we simply write this? Of course, this is not wrong. But just somehow in this textbook, Oppenheim and Schaefer, they prefer this notation just so that we have a consistent, a unified notation between DTFT and Z transform, right? Because if you regard X as a Z transform, right? then when it is evaluated on the unit circle, that gives you DTFT. So that's the reason why we have this special notation that instead of that, this is simpler. Okay, this is in a lot of situations, this is actually simpler when you make derivation. 做数学推导, so this is simpler, right? But the textbook uses this notation instead, so that we have a unified, 一个统一的, we have a unified notation system between Z transform and DTFT, emphasizing that DTFT is Z transform evaluated on the unit circle. Okay, that's an emphasis. 就是特别去强调这个等效性啊。All right, we have the unified notation for Z transform and for Fourier transform, the discrete time version. All right, so that's so there is also an analogy, right? So and similar now, may I ask a question? Now, the textbook also use this notation for continuous time Fourier transform, right? Why? Why do we need to write J here? Why is this notation preferred? Anybody? Why is this notation preferred? Why is this notation preferred? Okay. Laplace transform. Because now you have a unified, thank you. Okay, for those of you that are familiar with Laplace transform, how do we define it? X of S equals to summation, the integral x of t e to the minus st dt, right? So, so if we plug in j omega right here, then that becomes x of t e to the minus j big omega t dt. That's exactly the continuous time Fourier transform. Okay? So we have a unified notation between Laplace and Fourier transform. And by the same spirit, 同样精神. Similarly here, we have introduced this kind of notation in favor of being unified. Okay? So one nice thing to mention. Okay, yeah. All right, so notation definition, and then next thing is another definition. We are like throwing a lot of terminologies today. Okay, the next terminology is frequency response. The frequency response. We say frequency response of system. What does that mean? Again, for LTI system, that if the output, now we know that there's a system H which denotes the impulse response of an LTI system. And convolution theorem also holds for in the Z transform domain. Yeah? When we have two signals convolving in the time domain, in the Z domain, the transform multiplies. Okay? Small h convolve with small x, big H multiplied with big X to produce the output Z transform, the Z transform of the output. Okay? And so a few terminologies right here, actually. H of Z, okay? H of Z, which denotes the Z transform of small h, okay? Now we can call it the system function. There will be examples, okay? System function, and then when we evaluate, again, when we evaluate this Z transform on the unit circle, then this, as a function of frequency, is called the frequency response of the system, again, if it exists, okay? If the DTFT exists, then it's called the frequency response of that system. Okay? So let's organize our thoughts a bit. Okay? We have a system first. And the system is characterized by its impulse response. This is LTI. Okay? All you need to know is impulse response. Then we just take the Fourier transform. If it exists, then we call it the frequency response. So the frequency response, in short, just briefly speaking, what is frequency response of an LTI system? frequency response, the frequency response is the Fourier transform of the impulse response. Long story short, okay? Long story short. So far, so good. Okay, about these, any question regarding these definitions? Frequency response, 频率响应 frequency response. But then, what's the implication? What's the insight that we can learn right here? So it's like we have the input in time, and there is an LTI system denoted as H, and it produces YM. And we know that H is specified. H is characterized by its impulse response, and that's all we need to know about the system. Okay? Sure, Y will equal to X convolve with H. But there's another interpretation. We can go to the frequency domain first, and then calculate the spectrum. Okay? And then what will H do? Then after the system processes the spectrum, you can think of now the output spectrum equals to H, the frequency response right here. This is the frequency response function, which equals to H is it is the Fourier transform of impulse response. And then Y equals to the frequency response times X, the input spectrum at every frequency. Okay? So in the frequency domain, this is what is happening. Becomes multiplication. Okay? Convolution becomes multiplication in the frequency domain. And we might be able to agree that multiplication is an easier concept. It's easier to understand multiplication than to understand convolution, right? Can we agree on that? 小学时候有学乘法嘛，没有学 convolution. Right? I don't think I've learned that when I was in elementary school. So this is a rather easier concept in the frequency domain. But then after that, what can happen? If you ever wanted it, then we can take inverse Fourier transform to go back to the time domain. Okay, so that means Y equals to inverse dtft. Anybody? Inverse dtft. Okay, we can perform inverse dtft. Sure, from -pi to pi, and then Y equals to H times X in the frequency domain, and we synthesize the signal back to the time domain by collecting all the frequency components, okay? Quickly speaking. So that's the insight, okay? We have an LTI system, and we can first ask, then what does our input signal have at every frequency? That's its spectrum. The spectrum is a change of coordinate into the frequency domain. So every frequency has a magnitude, every frequency has a phase. Okay? But then now that in the complex plane, they are going to multiply with a frequency response. Okay? Going to every frequency, every component is going to multiply with the frequency response. So frequency response has two aspects. Let's come back to the slide. Okay? So here I do want to mention that when you write Y equals to H times X, please remember that H in general is a complex number. It's going to be a complex number. So here we are talking about multiplication of two complex numbers at every frequency. At every frequency, this multiplication is complex valued. 是复数的乘法. So that's an important thing to keep in mind. So we need to be a bit more careful about when we say frequency response. We can talk about the gain, we can talk about the phase. Okay? We can talk about the gain, we can talk about the phase. The gain, what is the gain? The gain is when we take the absolute value of frequency response. Okay? Right? Okay? 可能需要点时 Take your time, take your time. before I can continue. From here, okay, 1 over 2 pi, let's still keep developing this idea. Minus pi to pi, okay? So the gain we know that when we multiply two complex numbers, what's happening? What's going to happen? When we multiply two complex numbers, their absolute values will multiply. And how about their phase, the angle? The angle does not multiply, right? The angle add. The angle is summation. The magnitude is a multiplication when we multiply two numbers in the complex domain. So here, if we emphasize that here h equals to its absolute value times e to the j, the phase of itself. 这有点符号有点乱啊。But you get the idea. Yeah. Maybe I don't want to really emphasize this. Too much notation. Okay? Times x, which also has two parts. It's amplitude times e to the j, the phase part. And then we synthesize the signal back to the time domain by collecting everything in omega. So I'm just trying to say that the resulting signal right here will have this magnitude spectrum which multiply, okay? Then I'm just trying to say that the magnitude, or which probably is easier to go back here. Anyways, when we multiply two complex numbers, the magnitude multiplies and the phase add. So the output spectrum, at every frequency, the output spectrum is going to be equal to the input spectrum times the gain. That's why we call this the gain. Okay, that's why we call this the gain that the signal will receive at frequency omega. And how about the phase? The phase means a phase shift because x angle, the phase of x is going to be added with, because the phase of the spectral frequency response is going to add to the phase of x. And that's the result. The result is the phase of y at every frequency. Okay. Right, so I was trying to explain the meaning, the insight. What does it mean to have a magnitude response and a phase response? Okay, maybe let's just go over with this. The absolute value right here means again a signal will receive at any frequency omega, and the phase part means a phase shift because phase is adding. Okay, when we multiply in the complex plane, phase is adding, so it's a phase shift. A phase shift. So we can refer to these two functions as magnitude response and phase response of a system. Okay, that's probably maybe all I need to emphasize right here. Okay, so I do have an example. Okay, for example, here we have a system. Okay, we can take a look. This is a system receiving input X and producing output Y. Okay? Then where we have a factor right here, T, and that you can regard it as the sampling period for A to D and D to A conversion. Okay? So now, this is there are a few exercises that we can do. First, is this system causal? Is this system causal? And whether or not it's causal, we can try to sketch the system's impulse response. And from there, we'll be able to calculate the frequency response if it exists. And if it does exist, we can again then make a drawing of the magnitude response and phase response. Okay, so there are quite a few things that we can do from this simple example. So we can do it maybe for a few minutes. Let's write a few things down first, and then we continue our calculation when we return in the next hour. Okay, so let's do a few things first. Y equals to xn minus xn minus 1 divided by t. Okay, so the first thing is let's try to derive the impulse response. Okay, so now if this is h, and now if it receives the input delta n, okay, delta n, what is the output? That's a question. Okay, that's a question. So you can do this. N equals to 0, h of n equals to delta 0 minus delta minus 1 divided by t. Seriously, that's what you can do. Okay, so h0 is 1 over t. And n equals to 1, we'll stop right here, and then we take a break of 10 minutes. H of 1 equals to delta 1 minus delta 0, right, according to the definition, divided by t. And that's 1 minus 1 over t, okay? So, and so on, right? So this way we can make a sketch of the impulse response. By definition, when the system receives the delta function, the output it produces is called the impulse response. So we'll return and do the frequency response part after the break. Okay? Now. Okay, so yeah. All right, let's get back to this question, okay? This exercise. Let's get back to this exercise. So here we do have an equation defining the relation between input and output. And then we have tried to start sketching the impulse response, right? And so on. But very soon you may, one way or the other or another, you will realize that the impulse response consists of only two non-zero samples. These are the only two non-zero samples. Okay? One is located right at time zero. So if this is time, we have time zero. Now the impulse response h at time zero, it equals to 1 divided by t. And at time 1, it equal to the negative of that, minus 1 divided by t, where t denotes the sampling period. Okay? Yeah. And everywhere else is 0. 0 everywhere else. Yeah. Only two non-zero samples. So now we may ask a few further questions. Is the system causal? Is this system causal? Yes. Because the impulse response is what? The impulse response is all 0 before time 0. All 0 before time 0, yes, we have checked. It is causal. This satisfies causality. Okay? So first thing first, is the system causal? The answer is yes. And we have drawn the sketch right here for that impulse response. Now, second question right here. The second question, does the frequency response exist? Does the frequency response exist? Okay, so does the frequency response exist? And we need to ask the question, how about summation of n, of all n, right? Summation of all n, h of n, e to the minus j omega n. Does it exist for all frequency? And the answer is, of course, it exists. This is not even an infinite summation. Is that too quick? This is not even an infinite summation. We have only two non-zero samples, right? So, sure, the frequency response, which is the Fourier transform of the impulse response, if of course it exists at every frequency, because we are not even talking about infinite sum. There's no issue of convergence. The summing two part is actually really h of 0, e to the minus j omega 0 plus h of 1, e to the minus j omega 1. Of course, this converges everywhere. Okay, the z transform converges on the unit circle. Okay, right? So everybody clear, there is no issue of convergence. This is what we call finite impulse response. FIR is always stable. The Fourier transform always exists. Okay? Only two non-zero samples. Of course, there's no issue of summing infinitely many terms. 并没有在做无穷求和了啊，所以 Of course, the Fourier transform second question, my answer to the second question, does the frequency response exist? Yes. It exists. It exists. So now we know it exists. Let's plug in the number, shall we? Yeah, plug in the number. We have 1 over t, and this term is just 1, and plus minus 1 over t e to the minus j omega. That's the frequency response. Seriously, it's a function of omega now, right? So this expression is correct. Okay? This expression is the frequency response, and then, but the next thing is a bit more tricky. Okay, that's what I really want to show. Is the next thing. All right, this is a complex number. In general, this is complex number. Let's simplify it a bit. So there's a 1 over t factor that can be extracted. So inside we have 1 minus e minus j omega. Looks like that's the result we get. Okay, this is what we call the frequency response, a function of omega. Okay, the next thing is a bit more tricky. Now let's ask about what's the magnitude response and phase response. Seriously, okay, magnitude response we need to put in absolute numbers, right? No, absolute value 绝对值加上去啊 right? That's seriously what we mean, frequency response, magnitude response, okay? Which one do you want to show first? Magnitude or phase? But before I move on, okay, this is one way to derive the frequency response. But let's, before we fill in the details for magnitude and phase, there's another way, solution 2, which is worth mentioning. Yeah. Okay. Remember what this lecture, how we just learned is Z transform. We can also use Z transform. It's useful. Okay. Z transform can be used for derivation of frequency response. Why? Because frequency response is Z transform evaluated on the unit circle. Okay, so let's do that. Solution 2, starting with yn equals to x of n minus xn minus 1 divided by t. Okay, that's in the time domain. So let's take both sides of the equation to the Z domain, applying Z transform to both sides of the equation, shall we? Applying Z transform now. So on the left side, after Z transform, if I use script Z to denote Z transform, okay, 草写 Z, Z transform. Take the Z transform, the result, of course, is YZ, right? By definition, we don't even need to show it at this moment. But now, what's the Z transform of 1 over T now? X of n. When we take the Z transform of x, that becomes big X. Okay? And there's a property that when we shift in time by one sample in Z transform, that corresponds to 1 unit delay, okay? Which is denoted as you can easily show Z inverse. I call this Z inverse, 导数了, Z to the minus 1 power, 1 divided by Z, 一除以 Z. Z inverse, that's the way I call it, Z inverse X of Z. So that's a trick. Do this completely in the Z domain. That's a shift theorem. Shift by one sample to the right, you multiply in front with a Z to the minus 1 power. Okay? Z inverse. So far, so good? Is it clear? It's an important trick. Everybody should know it after taking DSP, all right? So please be sure you know this trick, okay? But then from there, if you can learn this, if you accept this, then this is cool. Then we have 1 over T, then we have 1 minus Z inverse times big X as a function of Z. Then, okay, then what's next? And by definition, Y by definition is equal to the system function times X of Z, right? So then simply, because Y convolution theorem, right? System function times the X, big X equals to big Y. Okay, so then what is the system function? H of Z. Can you tell me? H of Z is E 减掉 Z 负一 1 minus Z inverse divided by big T. Okay, scale by big T. Quickly. And we have all confidence. We have the confidence that this is going to be equal to the Z transform of the impulse response. So do we have the same result? Do we have the same result? Yeah. So that's a kind of a nicer trick I would like to share with you. Just use Z transform, and we will repeatedly come back to this. Okay? Important stuff. Everybody okay? Yeah, this is important. Very nice trick. And this really, H of Z, and then what else? Then what's the frequency response? What's the relation between frequency response and the system function? Frequency response is system function evaluated on the unit circle. Right? So therefore, just simply using this very nice notation, H of EJ omega, already by this notation, 如果够熟练的话, you are sophisticated in this notation. Immediately, by evaluating this system function on the unit circle, you get the frequency response of the system, which is 1 minus E minus J omega divided by T. Do we have the same result? Okay, do we have the same results? We have the same results. Okay, so contemplate. Yeah, let's contemplate on the two solutions. Okay. Different ways to reach the same conclusion. Okay, to reach the same conclusion. All right. Yeah. So now, with two different ways to reach the conclusion, now we have an expression for a consistent expression for frequency response. Let's calculate its magnitude and phase. Right? So the next thing I would like to go together with you guys is to calculate the frequency, the magnitude and phase. Yeah. To calculate the magnitude and phase. Yes. So this is our frequency response. So this is a bit tricky. So let me just elaborate this expression a little bit. Okay, I'm experienced now. What is e to the something, e to the j something, using Euler's formula, 尤拉公式, Euler's formula. E to the something, that thing is cosine omega. And there's a minus sign, there's a minus sign, so I think this is j sine omega right here. But now, instead of directly put the absolute value right there, our goal is to calculate magnitude and phase, right? But here I'm experienced, okay. What is 1 minus cosine? 1 minus cosine omega is what? Does it equal to 2 sine square something? Have you learned this in high school? 2 sine square omega divided by 2. I think that's the answer. But then what is sine? Sine omega can also be expressed as 2 sine omega divided by 2 cosine omega divided by 2. Why do I do that? Okay, the reason will become clearer. Okay, so I'm going to use these two identities, trigonometric identities, 三角恒等式. Turns out to be useful. They turn out to be useful. So if we just further proceed with our calculation, 1 over t, so we copy everything 1 over t, and now it seems that we have a factor of 2 cosine, 2 sine. We have a factor that can be pulled out, right? And then inside, we have sine what? Plus j cosine. Yes? So miraculously, this is what we have. Yeah? So far, so good? So 1 over t is still here. 2 sine omega divided by 2. But then what is here? This is a point on the unit circle, actually. This is just some very nice trick regarding this very exercise. Okay, not that important, but yeah, hold on, just bear with me. Bear with me. So what is this? I can write this as e to the j. Actually, it's pi divided by 2 minus omega divided by 2, right? Because ej something is cosine plus j sine, but pi over 2, that's 90 degrees, 90度减它正弦变余弦，余弦变正弦 Sine become cosine, cosine become sine. Okay, so I'm familiar with this example. That's why I can make this tricky derivation. Not that important. Okay, so this is great. So now we have more or less this becomes the magnitude, but not really, not quite. But that becomes the phase. Because this thing here is great. This is real, right? This function as a function of omega is real. And this as a function of omega, the phase, is each exactly in the correct form that we want. This format is exactly what we want. E to the j something, that thing is a phase spectrum, right? And in front we have a real thing. Good. That roughly speaking, that's the magnitude. Okay. Yeah. So that's kind of a trick. First, you don't absolutely need to follow me. Okay. You can try to just extract the phase directly from here. That's all right too. Okay. But this is just because I'm experienced. This is a very nice example, classic example, 非常经典的 example. So now we are ready to plot the magnitude response and the phase response. Okay, so the magnitude response is supposedly should be the absolute value of our frequency response. It's going to look like what? The result is 1 over T2 sine 那个东西啊。1 over T2 sine omega divided by 2. So how about when it goes to pi? That's the question. Okay? When it equals to 0, the magnitude equals to 0, right? And then it's basically going to reach to 2 divided by t, I think. Am I right? Yeah. 1 over t 2 times sine omega divided by 2. Okay? So it's 0 for frequency, 0 for DC. The gain is 0 for DC. And the gain reaches its maximum at Nyquist. That's really seriously, that's what we mean. Okay? The magnitude response of this system has a 0 gain at DC and maximum gain at the highest frequency, which corresponds to Nyquist. Okay? Pi is Nyquist. Okay? So that's the magnitude response. And how about the phase response? The phase response is equal to what? 90 度 pi divided by 2 minus what? Minus omega divided by 2, right? Omega divided by 2. So it's a straight line. The frequency response is a straight line. No, the phase response is a straight line, okay? Which equals to pi divided by 2, and then straight line zero with a slope, and it's a straight line, equals to 0 at Nyquist. So that's my solution, my quick sketch. Okay, we have a system, a discrete time system. Now we can talk about magnitude response and phase response. This is one example. Yeah. One example. Okay. Yeah. All right. Any comment right here? Yeah. Is everything clear? So this is the very first system that we look at together, okay? Very first systems we look at together. I've shown you how to derive the system function and frequency response more quickly, perhaps, in the Z domain. Z transform is useful, okay? Please understand that. Z transform is helpful. And then later, that trick is not absolutely important, but here, with that trick, I was able to show the magnitude with zero gain and maximum gain, a straight line for the phase response. Okay, so I do have a remark. Okay, any questions so far? Any question, comment regarding this example? Does it make sense? Is it making sense? Is it making sense to you that DC gain is 0? DC gain is 0. Okay, does it make sense? Does it make sense? DC gain. Let's contemplate the result. Okay, the DC gain is 0. Is it making sense? I like this question. Is it making sense? I think it makes sense because when we have DC and we are subtracting the previous example, previous sample from the current sample, the result comes out 0. Okay, everywhere. So the gain is 0. Okay, in that regard, it makes sense. Okay, but then I want to share with you that I call this system numerical differentiation. 数值微分 This is the way I would call it. Now, this system can be called numerical differentiation. Why? Anybody want to guess why? Why am I calling it numerical differentiation? 数值微分 in what sense? In what sense do we call the system numerical differentiation? Differentiation can only happen in continuous time, right? But in discrete time, we can approximate it. In discrete time, we can approximate time derivative by just subtraction, just delta x divided by delta t. That's what I mean. Do you notice that this is delta x, right? The change, the amount of change in x after one sample. When time proceeds from n to n minus 1, what's the change? So this, in a sense, this is the amount of change in x. Okay, divided by this little short time t, right? Sampling period is a short time. Okay. So this is really the meaning is delta x divided by delta t. Yeah. That's what the system actually is doing. So again, to contemplate on our result, what this system does, y of n equals to x n minus the previous sample, that's a change, right? That's a change, and t is the amount of change in time. So in that regard, this is like delta x divided by delta t, something like that. Something like that. And we know that when delta t approaches 0, then it's essentially calculating a numerical calculation of differentiation, 变成数值的微分的数值逼近了啊。Is that clear? Does that make sense? Is it making sense? All right. So if it makes sense, delta x delta t. This is just before we know that. Note that limit delta t approaches 0, delta x delta t is basically the definition of dx dt. So that's why in this sense, I'm calling the system numerical differentiator. So if this makes sense, then now we can interpret what's going on right here. What's going on right here? DC, because when you differentiate DC, the result is 0, right? So it makes a lot of sense. When you just take differentiation, numerical or not, differentiating a constant, the result should be 0, right? This makes sense. The DC gain is 0, according to our calculation. And what else? We all learned that when we differentiate a signal e to the j omega, let's say if the continuous time is e to the j big omega t, and we take d dt, what do we have? The gain differentiation enhances high frequency. 高频的部分被增强。There's enhancement of high frequency when we take the time derivative, right? So the gain should be proportional to the frequency if we want to numerically approximate what's going on in differentiation. Okay? Because in continuous time differentiation, no doubt, there's no doubt this is rigorous. Right? Take the first derivative of a fixed frequency signal, yeah, a signal with a constant frequency, and take its derivative with respect to time, you get this. And that's a gain, right? That's a gain. Or the absolute value of that should be the gain. The absolute value of that should be the gain. Therefore, the gain, what we are trying to approximate, we want to approximate this idea that the gain should be equal to j omega, which is basically omega, okay? Omega is a gain in continuous time. But now, when we go to discrete time, how good is our approximation? How good is our approximation? Is this a good approximation, at least for low frequency range? No? So I said this is nice because now at low frequency, if we talk about like this frequency range, then the gain function almost looks like a straight line. So we're talking about here, right? Therefore, when omega is much less than pi, at small frequency, then 1 over t 2 sine omega divided by 2 is approximately 1 over t 2 times omega divided by 2. Because when omega is small, sine of it is approximately the angle itself. Sine theta approaches theta when theta is small, right? 2 and 2, then further omega divided by big T. And then what is omega divided by big T? That's big omega, right? So don't we have a nice correspondence between discrete time approximation and the continuous time prototype? Okay, so this system is a approximation of differentiation. Right? It's an approximation of trying to estimate velocity when you have displacement, and it's a approximation of trying to derive the current when you have the charge. Yeah, seriously, that's what it is. Okay? It has a very nice frequency response in terms of magnitude. At least as far as magnitude is concerned. Okay? As far as magnitude is concerned, when frequency is small enough, indeed the gain roughly approximates is what should happen back in continuous time. Okay? So there are a lot of things to contemplate. 所以就常常来凝视一下我们的答案。Contemplate our results to see if everything makes sense. Yeah? Okay, so I was trying to say that, just one last remark to conclude this slide, okay? If x is displacement, so y is velocity. Okay? If x is the charge on a capacitor, then y is the current flowing out of a capacitor. So this really, seriously, that's a good way for approximating the dynamics. Approximating what's going on when we take take the first derivative of one variable in discrete time. Okay, it's a good approximation. We can call it a numerical differentiator. Yeah. Okay, so with that, let's finish this lecture. The next lecture, which we're also going to begin today, will be about difference equation. And then in solving that, we will use Z transform. And second point is not that important. I'm really fond of this topic, by the way. You can tell I'm really fond of the topic of linear time invariant systems. I like it so much, so I named myself linear time invariant on both Instagram and last year Thread. So you can find me. My name is linear time invariant. Thank you for attention. Right, thank you for attention. All right, so let's take a break of maybe like 2 minutes to the next lecture. Right. I mean, there are so many people are good DSP engineer, but only I am linear time invariant. Okay, I'm extremely proud of that. Okay, my Facebook account is something else, though. Yeah. Don't try to find my Facebook using that. Okay, I have a different ID. 帮我擦一下黑板啊，两边都擦好。那个要照相的话快啊，我请助教擦黑板啊。So any third users right here? 同学间 or you use DCOP 比较多的 different purposes. I stopped using it a few months ago. But I had one really silly post, and it somehow 有戳中 the algorithm. I got like 940 likes in 2 days, and I post the same thing on Facebook and Thread. I synchronized it. Then my Facebook post received only like 40 likes among my friends, but in the meantime, Thread pushed it to 900 users. I thought that was ridiculous, so I stopped using it. But I still keep the account, but I just deleted the app from my phone. Anyway, yeah, so next topic, right? It's kind of funny, yeah, about Thread, all these social medias. So I found sometimes they receive new users. Like, like in the US, after the election, a lot of people quit X. Have you heard of that? Yeah. 很多美国人离开 X， 因为他们受不了花式供养。So they wanted to find some alternative social media. So one of the things they tried is Thread, but it didn't really. 美国人其实没有用不太起来。So they still struggle. So good luck for Americans. Next lecture. Now finally we can talk more about difference equation. We have just seen a few examples, right? Difference equation with constant coefficients, and we emphasize that they are linear. And I do have a subtitle for this lecture. Okay, the main title is indeed LCCDE, linear constant coefficient difference equation, LCCDE. That's the main title for sure. But I do have a subtitle. we want to limit our interest on using these equations causally. Okay, so that's sort of a warning. 这个有点算是警语啊。Use with discretion. Yeah. I recommend using difference equations in a causal way. Okay, what that is, it will be clearer when we touch base on using difference equations, how to use them. All right. So, two sections. The first section, I'll talk about general scope and formulation. What is a difference equation, right? And then just the second half is about the Fibonacci sequence. Fibonacci sequence is what? 1, 1, 2, 3, 5, 8, and 13, and so on, right? Every new term is a summation of the previous two terms. That's a Fibonacci 费氏数列, Fibonacci sequence. Turns out that we can write down a difference equation which produces Fibonacci sequence. Okay, so I think that will be a very nice example for a lot of discussion. Okay, so that's like the two sections for this handout. So the first thing, general scope, let's begin with definitions. Okay, so just take a look at this equation. So again, if x is the input, then we can define such a relation to calculate current output. Okay? At every time n, we will look at the input to n samples in the past. K sums from 0 to big N, right? So it goes backward. K is here. K goes backward. Okay? So this sample, previous sample, n samples in the past. Okay? And there's a linear combination right here. And similarly, we also look back. Look what the system already produces in the past. Okay? So again, here we generally, if you look m samples to the past and linearly combine the past so that this is the current output. And you can imagine that this is something that can be implemented with a computer. Right? This is like one line of your code in C, in Python, in MATLAB. Right? This is like one line of code. Okay? You can imagine the setup of your memory. Just memorize, the system should memorize m samples to the past. And then also memorize n sample of the input in the past. Then just linearly combine them. Here we do emphasize that the coefficient right here, a and b, they are real value constants. Okay? That means the system is going to be time invariant because the behavior does not change. A and b are constants. Okay? Now all the coefficients here are constant. It's a time invariant system, and everything's linear because there is no square term. Everything's linear. It's indeed a linear time invariant system, LTI, constant coefficient. Now we call them, you can also refer to them as LCCDE. Yeah, not that important, LCCDE. Linear, C constant coefficient, CCDE difference equation. Okay. So that's the definition. That's the definition. But then we can show quickly. This is rather quick, okay? But let's try. Give it a try. Let's try to see that if this is in a time domain, then in the Z domain, if you take the Z transform, again, similar idea. Take the Z transform on both sides of this equation 1, okay? Let's try it. If you take the Z transform on both sides of equation 1, then small y immediately become big Y. That's on the left-hand side of the equation. That's what we should put. Right? But what is happening going on the right-hand side? On the right-hand side, we have summation. Now K is the dummy index, goes from 1 to big M. And minus AK is the constant coefficient, but then Y delayed by K samples. What does it correspond to in the Z domain? That's the question. That's the trick, right? Y delayed by K sample corresponds to Z. There's a Z to the minus K in here, corresponding to K samples of delay and big Y. z. Okay, because that's a z transform. That's a z transform of y delayed by k samples. Okay, so that's the trick. And then next term is very similar. We have a summation. K now goes from 0 to big N. And bk constant x delayed by k sample again. So let's practice one more time. Delayed by k samples correspond to this term in z domain. And then multiply by xz. Okay? So with that, we can, what's next? We can move all the things corresponding to y to the left-hand side with a change of sign. Okay? We can move it to the left-hand side. Then on the left-hand side, we have 1 plus a1 z inverse plus a2 z to the minus second power all the way to a sub big M z minus big M times yz. That becomes on the left-hand side. If we move everything to the left-hand side, right? That becomes the left-hand side, right? So far, so good? Everybody with me so far? Yeah? That becomes the left-hand side. On the right-hand side, what remains right here is even simpler. It's basically b0 plus b1 z inverse and so on. B, the last term right here, big X in the z domain. So you see that z transform is useful, okay? You can just useful trick. Delay by k samples, z to the minus kth power, okay? Just put it right there. You put them right there, then now it seems that y of z, now y of z and xz becomes linearly related in the sense that if we think by definition y of z is system function times x of z, right? Then what is system function? What is the system function? The system function becomes, by definition, the system function should be defined as yz divided by x of z, right? And what is it? Just what is it? Then the system function yz divided by x of z becomes equal to this. Need to be careful. Summation b k z minus k, where k goes from 0 to big N, divided by summation k goes from, it's actually 1 plus k. Basically, I'm showing the same information. Okay, now let me just finish writing first. Okay. So basically, this is we are just saying that y times that equals to x times that. We're just basically saying that 交叉相乘. Okay, y is a cross product. Y times that equals to x times that. And this will appear so many times, so that throughout the semester we are going to introduce this notation. We're going to call the bottom here the denominator, 分母 denominator. The denominator we go to the bottom here, we refer to them as a of z. And on top, the numerator, 分子, this expression is going to be referred to as b of z. It will come just show up so many times. So here is a bit of the notation and definition right here. Okay, so a lot of information right here. Let's make sure that we are okay. Make sure we are okay. All right. Yeah. So that I'm pretty sure that in the end you'll be so familiar with this that once you look at this equation, automatically you can think of the system function as there are two polynomials, one divided by the other. Okay, top called b, bottom calls a. Right. Two polynomial 多项式啊 there's a few terminologies I can introduce. Polynomial. Polynomial. So this is going to be defined just simply called B of z, A of z. And both of them are polynomials. And this is an important result. Okay? Starting with a difference equation and ending with a rational expression of where there are two polynomials. One on top, one at the bottom. Okay? BZ divided by AZ is a general expression for all such kind of linear systems. Characterized by difference equations, right? So far, so good? So later, when we come back next week, we ask a few key questions. All right, so now, apparently, if you look at the polynomials, really, polynomials have coefficients, 多项式的系数嘛, the coefficients are simply those same coefficients in the difference equation, linear constant coefficient. These are the coefficients, right? And they specify B of z and A of z, right? So now with this formulation, 这样的架构, with this formulation, does it help us calculate the impulse response of any given linear system, any given difference equation? Given the LCCDE, we may be interested in calculating the impulse response. Turns out that yes, the answer yes. There is a systematic way of calculating the impulse response in closed form. There will be a closed form solution for any difference equation with constant coefficients. Okay? Much like differential equation. Wave function, there's closed form. Constant coefficient, differential equation has closed form solution. Cosine, sine 这些东西啊 yeah. So we asked a similar question. Given the coefficients, then how? The matter is not is how. How do we calculate the impulse response? Which is which corresponds to this system function, right? Yeah. And there's a second issue. Sometimes we worry that the system is not stable. You give a delta function, then the response explodes. It could happen. It could happen in the Fibonacci series. It doesn't converge, right? So then how do we ensure systems is stable? And in what sense? This is one issue that we need to touch base on. Yeah. And the second question, a short answer for us to kind of memorize. Okay, let me just invite you to simply memorize the result for now. I will explain. The answer to the second question is that it's all about the roots of these polynomials, of A of z. Okay, the root of A of z turns out to be important. They all need to be inside the unit circle for the system to be stable in a certain sense. Okay, that's a key result that we want to deliver. We want to make sure everybody gets this. Okay, stability requires all the roots of A of z to be inside the unit circle. Okay, any root, if root means A of that thing is 0, root,根啊. All the roots must be inside the unit circle. And we'll explain by example, by that Fibonacci series example. Right? So I think that's all I want to talk about for today. So next week, when we come back, we will officially talk about this system of we have y, the feedback term, as well as the input on the right. Okay, so that's when we come back next week. And see you tomorrow. See you tomorrow.